Hi folks! In this second video about stereochemistry, I'm going to be talking about optical activity and enantiomers. Recall that enantiomers are molecules that are non-superimposable mirror images of each other. Enantiomers will have identical physical properties. For example, here look at two chiral alcohols. Notice these have the same connections of atoms, but in one case the OH group is wedged, and in the other case it is dashed. These are enantiomers of each other. This molecule on the left has R stereochemistry, and the molecule on the right has the S configuration instead. Both enantiomers of this alcohol have an identical boiling point of 100 degrees Celsius, and they also have identical densities. But a property in which these enantiomers differ from each other is if they are exposed to what is known as plane polarized light. We'll use the fact that chiral compounds will rotate plane polarized light in an experiment known as polarimetry. A polarimeter is the instrument that measures how samples rotate light, known as measuring the optical rotation of your sample. At one side of the polarimeter is your light source. And this is just a typical light bulb that puts out randomly oriented light waves. This light gets passed through a polarizer, which has little tiny slits aligned along one axis. This polarizer aligns the light waves in one plane, and the light waves that aren't aligned along this plane do not pass through it. After the light has come through the polarizer, we would call it plane polarized light. And notice only those vertical light waves passed through this particular polarizer. Next, the light gets passed into a tube containing the chiral sample. What's interesting about chiral samples is that they cause this plane polarized light to rotate. Notice I've shown my light waves as no longer being vertical, but now skewed. After the light has passed through the chiral sample, it retains that same rotation that it developed while it was passing through the sample. If the particular chiral compound rotated the light clockwise, we give that a plus sign. And if the chiral sample rotated the light counterclockwise, we give that a minus sign. Eventually, the light reaches a detector which allows us to know how much it was rotated and in what direction. If the plane polarized light is rotated clockwise by the sample, we call that a dextrorotatory rotation, or a dextrorotatory sample. And if instead that plane polarized light was rotated counterclockwise by that particular chiral sample instead, you would call that levorotatory. I want to give you some terminology for how we describe samples for this type of experiment. We'll call a sample optically active if it rotates plane polarized light. A chiral sample will be optically active. A sample will be called optically inactive if it does not rotate plane polarized light. And achiral samples will be optically inactive. All chiral molecules are going to be optically active in some way. I want to talk about how we measure the extent to which a sample rotates plane polarized light. This will have a magnitude as well as a direction, positive or negative. An important thing to know about enantiomers is that they will always rotate plane polarized light by equal amounts, but in opposite directions. So if one enantiomer had a plus 20 value, and I'll explain what this means shortly, the other enantiomer would have a minus 20 value. What you measure in the lab for your rotated plane polarized light is known as the observed rotation. This is given the symbol alpha. This is your measured angle of rotation for a particular sample, and this depends on a couple of factors. This observed rotation will depend on your sample concentration. This will appear as the letter C in an equation below. And the observed rotation also depends on the distance the light travels through the sample, known as the path length. This is given an L symbol below. There's also a term known as specific rotation. This is alpha in brackets with a 20 and a D written by it. I'll explain these in a second. This is a benchmarked value that you could tell to other scientists around the world. These values are reported under standard conditions so that anybody can replicate them. The specific rotation is independent of concentration or path length, unlike the observed rotation I talked about before. And specific rotation is unitless. The equation that relates specific rotation and observed rotation is that the specific rotation is equal to the observed rotation divided by the path length times the sample concentration. The D stands for the fact that a sodium light source is being used in this measurement. And the 20 is the typical temperature in degrees Celsius that the experiment is run at. The path length L is reported in units of decimeters. This is 1/10 of a meter. And concentration is given in grams per milliliter. Let's return to our R2-butanol and S2-butanol molecules from before. These are enantiomers, or non-superimposable mirror images. The specific rotation of each compound has been measured, and for R2-butanol, this value is negative 13.9, and for S2-butanol, this value is positive 13.9. There is absolutely no way, except for measuring it, that you could predict the size of this value or even its sign. It just depends on your particular sample. But notice that these two values for my enantiomers are equal in magnitude, 13.9, but opposite in direction. One is negative, one is positive. This will always be true for enantiomers. You can write the sign that the light was rotated in front of the name if you want to. So because the specific rotation was negative for R2-butanol, the name could be written as negative R2-butanol, and then the opposite for the S molecule. The specific rotation was positive, so you could put a plus sign in front of the name. I want to talk about how samples will change depending on if you have a pure chiral compound compared to a mixture of enantiomers. I'll use the term optically pure to describe a pure sample of a single enantiomer. The term racemic mixture describes a sample where you have equal amounts of both enantiomers present. A racemic mixture, even though it contains chiral components, the racemic mixture itself is optically inactive. meaning your mixture will have an observed alpha equal to 0. If you have a sample containing both enantiomers, but not a perfect 50-50 mixture of the two, that sample will be optically active, but the observed alpha will be diminished compared to the alpha for the pure enantiomer. Let's consider our 2-butanol enantiomers again. Imagine two extremes. On the far left, you have 100% R2-butanol, and on the far right, you have 100% pure S2-butanol. Then in between these two values, you have varying percentages of the two present. Exactly in the middle of the diagram would be if you have a 50-50 mixture of R and S-butanol enantiomers. You would call this a racemic mixture, and the observed rotation alpha for this 50-50 sample would be 0. The minus 13 and the plus 13 perfectly are canceling each other out. Now let's consider that you have more of the S2-butanol present than you have R present, but it's not 100% S enantiomer. If you have more of your S enantiomer present compared to the amount of R enantiomer, your observed rotation alpha is going to be less than 13.9, but greater than 0. The exact number depends on exactly how much more S enantiomer you have. Alternatively, you could have a scenario where you have more of the R configuration than the S. In this case, your number will be somewhere between negative 13.9 and 0. Here as well, your exact number will depend on just how much more R enantiomer you have. So let's say you took a measurement of 2-butanol and you observed a rotation of positive 4.7. Because this value is positive rather than negative, you can conclude that you have more S2-butanol present. This is based on the knowledge that S2-butanol has a specific rotation of positive 13.9. So if alpha has the same sign as that, you have more S than R present. But we want to know exactly how much more. I'll define a term known as the enantiomeric excess, also known as %EE. This is a measure of how much more of one enantiomer you have around relative to the other. You're going to take the absolute value for your observed rotation, alpha, and divide that by the absolute value of the alpha for the pure enantiomer. Then multiply that by 100. For the specific example where you have alpha equal to positive 4.7, you would take 4.7, divide by 13.9, and multiply by 100 to calculate 34% EE, meaning you have 34% excess of the S configuration enantiomer relative to the R configuration one for this particular sample. To summarize, this video talked about the fact that enantiomers rotate plane polarized light, and they will rotate that light by the same amount but in opposite directions. I talked about how polarimetry is performed, samples being optically active or inactive, and I talked about the concept of enantiomeric excess. That's it for this video. I will see you in class.